The theory of relativity, one of the cornerstones of modern physics, fundamentally changed our understanding of space, time, and gravity. Formulated by Albert Einstein in the early 20th century, this theory is divided into two parts: special relativity and general relativity. Special relativity, introduced in 1905, revolutionized the concepts of time and space by asserting that the laws of physics are the same for all non-accelerating observers and that the speed of light remains constant, irrespective of the observer's motion. General relativity, presented in 1915, extended these ideas to include gravity, describing it as the warping of space-time by mass and energy. Einstein's insights resolved many perplexing issues in physics and laid the groundwork for countless advancements, making the theory of relativity a pivotal achievement in scientific history. Special relativity is one of the two pillars of Einstein's theory of relativity, revolutionizing our understanding of time, space, and energy. It primarily deals with objects moving at constant speeds, particularly those moving close to the speed of light. One of the key principles of special relativity is the constancy of the speed of light. According to Einstein, the speed of light in a vacuum is always constant, regardless of the observer's motion or the light source. This was a radical departure from classical physics, which assumed that velocities should simply add up. This brings us to the concept of time dilation. In the realm of special relativity, time isn't a fixed entity. Instead, it's relative and can vary depending on the speed at which an object is moving. The faster an object travels, the slower time passes for it relative to an observer at rest. This phenomenon was starkly illustrated in the famous thought experiment known as the twin paradox, where a twin traveling near the speed of light ages more slowly than their sibling on Earth. Length contraction is another fascinating consequence of special relativity. Objects moving at high velocities appear contracted in the direction of motion when observed from a stationary point. This means that to an outside observer, a spaceship traveling at near light speed would appear shortened. Several key experiments have validated these principles. The Michelson-Morley experiment, conducted in the late 19th century, showed that the speed of light remained constant, laying the groundwork for Einstein's later developments. Furthermore, experiments involving high-speed particles and accelerators have demonstrated time dilation, as particles moving rapidly decay more slowly than their stationary counterparts. In essence, special relativity reshapes our intuitive notions of time and space, asserting that they are interwoven into a single continuum known as space-time. Understanding this allows us to delve deeper into the nature of the universe and forms the basis for many contemporary technological advances and scientific discoveries. General relativity, proposed by Albert Einstein in 1915, revolutionized our understanding of gravity. At its core, the theory posits that gravity is not a force between masses, as Newton had suggested, but rather a curvature in space-time created by the presence of mass and energy. Imagine space-time as a flexible fabric that gets distorted whenever a massive object like a star or planet is present. This curvature affects how other objects move, guiding them along curved paths that we perceive as gravitational attraction. A central concept in general relativity is the equivalence principle. This principle states that the effects of gravity are locally indistinguishable from acceleration. In simpler terms, if you were in a sealed room without windows, you wouldn't be able to tell whether the force you feel is due to gravity or because the room is accelerating upwards. This idea paved the way for the revolutionary insight that gravity and acceleration are deeply intertwined. One of the most famous implications of general relativity is the prediction of black holes, regions of space where the curvature of space-time becomes so extreme that nothing, not even light, can escape from them. The theory also predicts the phenomenon of gravitational waves, ripples in space-time caused by massive objects moving. These waves were directly detected for the first time in 2015 by the LIGO collaboration, a century after Einstein first predicted them. General relativity has been tested and confirmed through numerous experiments and observations. For example, the bending of light from distant stars by the sun's gravity, observed during a 1919 solar eclipse, provided one of the earliest confirmations of the theory. This bending of light, a phenomenon known as gravitational lensing, allows us to study objects in the universe that would otherwise be invisible to us. In summary, General relativity provides a profound and accurate description of gravity, explaining everything from the orbit of planets to the behavior of light in the presence of massive objects. Its implications stretch far and wide, fundamentally altering our understanding of time, space, and the universe itself. Einstein's theory of relativity has had a profound impact on modern science, revolutionizing our understanding of the universe. In physics and cosmology, it provided the framework for explaining phenomena that classical mechanics couldn't, such as the behavior of objects at high velocities and the warping of space-time by massive objects. This led to the realization that space and time are intertwined and dynamic, rather than fixed and immutable. One practical application of the theory is in the Global Positioning System, or GPS. GPS satellites orbit the Earth at high speeds and experience weaker gravitational fields compared to those on the surface. According to relativity, these conditions cause the satellite clocks to tick faster than those on Earth. Without accounting for these relativistic effects, GPS accuracy would drift significantly, rendering it useless for navigation. The theory of relativity also revolutionized our understanding of black holes. General relativity predicts the existence of these incredibly dense objects where space-time is so distorted that nothing, not even light, can escape their gravitational pull. Observations of black holes and their interactions with surrounding matter confirm these predictions, providing strong evidence for the theory. In summary, Einstein's theory of relativity is not just a theoretical construct, but a crucial part of our technological world and cosmic understanding. It bridges the gap between the very large, like galaxies, and the very small, like GPS systems, illustrating the interconnectedness of all things in the universe. Einstein's theory of relativity, despite its profound insights, has not been without its share of challenges and misconceptions. One common misconception is that relativity states everything is relative. In reality, it introduces specific non-absolute frameworks for understanding space and time, yet posits invariant laws of physics and the constancy of the speed of light across all frames of reference. A significant challenge in the theory's acceptance was its radical departure from Newtonian physics, which had dominated scientific thought for centuries. When Einstein proposed special relativity in 1905, the notion that time and space are not absolute but relative was difficult for many to grasp. It contradicted everyday experiences and intuitive understanding of the world. Misunderstandings also extend to time dilation and length contraction. Many falsely believe these effects are merely theoretical. However, they have been experimentally verified through observations such as the decay rates of muons traveling close to the speed of light and precise measurements involving atomic clocks on fast-moving aircraft. General relativity, introduced in 1915, faced even more skepticism due to its complex abstraction of space-time curvature. The idea that massive objects warp the fabric of space-time challenged the conventional understanding of gravity. Einstein's theory wasn't widely accepted until 1919, when Arthur Eddington's expedition confirmed the prediction that gravity bends light during a solar eclipse. Overall, debunking these misconceptions and overcoming initial resistance required rigorous experimental evidence and a paradigm shift in physical sciences. Such challenges highlight the groundbreaking and transformative impact of Einstein's work in expanding our understanding of the universe. As we wrap up our exploration of the theory of relativity, let's recap the journey we've taken. We began by delving into the foundational concepts of both special and general relativity, shedding light on the groundbreaking work of Albert Einstein. We then explored special relativity, highlighting the revolutionary ideas about the constancy of the speed of light and time dilation, supported by key experiments. Moving on to general relativity, we unraveled the intricate nature of space-time curvature and the equivalence principle, reshaping our understanding of gravity. Additionally, we discussed its far-reaching impact on modern science, from revolutionizing physics and cosmology to practical applications like GPS technology and insights into black holes. Finally, we tackled common misconceptions and the initial challenges faced by the scientific community in accepting and proving the theory. The theory of relativity stands as a cornerstone of modern science, continually inspiring and guiding our quest to comprehend the universe.